second video dealing with the problem solving of colligative properties. We'll clarify what types of problems will we have to apply these equations for. So really, this week we are just looking at, the molality, which molality really has the greatest role whenever we're looking at colligative properties, otherwise molarity. So boiling point elevation, freezing point depression, what could we be asked? So I found this great summary that I've included the document below this video if you'd like to print it out or take a look at it for yourself. You also, of course, can pause and then zoom in and take a look closer. But this is, again, a summary of colligative properties. But in Honors Chem, we just look at the impact a solute has on a solvent's boiling point and freezing point. So here's just a nice summary of what you've already been shown in previous videos, and a little bit more about the Van Hoff factor. Now, what kinds of things could we be asked? We often are going to have to find the boiling point of a solution. You may be directly given molality, and of course, you will be able to find or be told in the problem the Kb value, and you will know your solute and then be able to interpret the Van Hoff factor. So often, we're asked for the boiling point. Well, what else? Here's another boiling point question, but it is dealing with a solute that will dissociate in solution. Now, sometimes they loosely use the term ionization. We know better. Ionic solutes dissociate. This, however, a covalent solute. Now, you may or may not be told this, so you have to know. Now, this is covalent molecular, so we know the Van Hoff factor is 1. But here, the Van Hoff factor will be 3, and so that will apply and make a difference, of course. So you could be asked to find the new freezing point, the new boiling point. You also could be asked to find molality if you know what the new boiling temperature is or what the change is. And so here's an example. For this year, we will not be asked for molar mass, but that is something else that we could be asked for, but not for us in the spring of 2020. All right, so there's some example questions and work. I would like to walk us through these two examples. All right, so remember these are our equations, and you can trust that this information, if we need it, will either be given in the problem or you can access it in the table that I provided on this page. All right, so first thing, we're going to look at this example 11. What is the boiling point? Okay, so immediately I know, all right, delta TB equals Van Hoff factor, KBM. I know that if it's asking me for the boiling point, I'm going to have to find the change in the boiling point and then apply the change to the pure solvent boiling point. I have dissolved 31 grams of sodium chloride. And sodium chloride, ionic. I know when that goes into solution, you don't have to write the dissociation equation. But for every one of these, we will get 1 sodium ion and 1 chloride ion. So I know my Van Hoff factor is 2. We're told, that should be dissociation. Oh, be forgiving. In 559 grams of water. That is my solvent. For this equation, I need the Kb value because I'm boiling. And the Kb value of water is 0.51 degrees Celsius per molal. Now again, you'd either be given this in the problem or you can access it from this given table. We're dealing with water as the solvent, and I pray that we just know the boiling point is 100 degrees Celsius. This should not limit our sig figs. We're pulling this from our memory, of course. All right, so I just need to plug and chug and obey the equation. So my Van Hoff factor here is 2. The Kb for water, 0.51 degrees Celsius. Now it's definitely okay if you just put per molal. But I can see I'm going to have to find the molality. So I'm going to go ahead and expand molality to be mole of solute per kilogram of solvent. Okay. And if you want, you can put this over 1 so we can see, the conversion factors that are emerging. Now, I'm not overtly given the molality, but I sure do have everything that I need to find it. Molality is mole of solute in my numerator. I'm not given mole of solute. I'm given grams of solute. So I know I can just rely on formula mass. So adding up sodium, 22.99 gram per mole, plus my chlorine, 35.45, I get 58.44 grams in every 1 mole. Okay, so far, that cancels grams of solute. Now I'm in moles of solute, and that will cancel here, numerator with denominator. But it's not mole of solute, it's molality. So I need this per my mass of solvent. So just like we're free to put this over 1, we can put the information of our solvent, but we of course need it to be kilograms. And so we'll do one more step. And then we have mole of solute per kilogram. That will cancel that. And then I'll just have degrees Celsius as my final unit. So just plugging and chugging and doing my work. All right, so we get, and this comes from experimentation. So it could limit us to 2 sig figs, but we have 2 here and 3 there, so we're limited to 2. And I get 0.97 degrees Celsius. Let me just double check my work. Yep, 0.97. Okay. Now this is my change. So if we were just asked for the change in the boiling point or the boiling point elevation, that's it. But we want the solution boiling point. So you take the pure boiling temperature, the pure solvent, and we know it's boiling point elevation. So the boiling point of your solution will be higher. We will add that 0.97 degrees Celsius. So the solution boiling point, there we go, 100.97. Now, because sodium chloride dissociates, because it is an electrolyte, well, which makes it an electrolyte, but because it dissociates, that amount of sodium chloride has twice the impact, twice the number of solute particles that can raise the boiling point in this case. So that is 11. That is your final answer. Okay, number 12. Calculate the freezing point. All right, so I know I'm dealing with this. I'm asked for the freezing point, so I know I'll have to find the change and then apply it. Of a non-ionizing antifreeze solution containing 388 grams of ethylene glycol, and that is C2H6O2, and 409 grams of water. All right, so we know that this is in the greater quantity, and so water is our solvent. We're asked for freezing point. Okay, the freezing point, pure water, we know is 0, and this would not limit our sig fig, so if we needed to carry it further beyond the decimal place, we need the Kf for water. Again, you'll be given the problem, but can access it. And remember, sometimes your Kf values are given as negative values, but not always. And this is per mol. Okay, so let's plug and chug. Now, they told you in the problem, but you need to be able to conclude yourself, because this is a covalent molecular solute, does not dissociate or ionize. Van Hoff factor is 1. So our I value is 1. Our Kf, negative 1.8 degrees Celsius per mole of solute per kilogram of solvent. And we will just set it up so similar to what we did in the previous problem. The main difference is a dissociating versus a non-dissociating or non-ionizing solute. So the rest is the same. We need to get the molality. Well, my solute delivers this mass, but I need moles. Excuse me. So, I just need to find my formula mass. And we will get 62.08. Let me just double check that so quickly. Yep. And that will get us mole of solute, to cancel that. But we need it per kilogram of solvent. And we are given 409 grams of water. Just like you can put this over 1, we can put that under 1. And we need to get ourselves to kilograms. So, doing that, we'll cancel that, and we'll have degrees Celsius. All right, and we get, I'm going to double check my math on that for sure. 3 sig fig, 3, 3. So I can report 3. Now, this is a pretty high concentration of solute. Oh, yeah. So negative 28.4 degrees Celsius. So the new freezing point, we take the pure solvent and then make sure the solution will be a lower. So we are fine to add that negative change in temperature that we found. So this solution will freeze much below the pure solvent, which of course we use antifreeze in many mechanical systems to prevent the freezing and then expansion of water, which could cause not only breakage of tubing and pipes, but also stop the liquid from flowing because it would be in the solid state. So that is 2 examples for us, as well as some just targeting of what could we be asked with these colligative property equations. So we will be applying these to find a solution boiling point, a solution freezing point. We also could be asked to find molality most commonly. Best of luck.